Hello everyone, thanks for joining. Thanks for listening to this webinar. This webinar is about VibeSys, a new software for acoustic and vibration analysis. My name is Fred Kim. I'm in charge of promoting VibeSys, and we'll spend the next 20 or 30 minutes together discussing or introducing, say, what VibeSys does, and I'll end up this webinar with a little demo of how it looks like. So you've got my email address here. Feel free to contact me for any specific question. So let's go. VibeSys then. You know that nCode is a software provider of Design Life, the FEA based fatigue analysis software. You have probably heard of GlyphWorks, so that's an analysis software for durability, test data. Automation is a database, an engineering database, enabling you to easily get gold information from terabytes of data under the form of a table or of a graph to understand trends, etc. Now we've got VibeSys, which is a dedicated software to the analysis of acoustic and vibration. So VibeSys has the same benefits of GlyphWorks or Design Life, if you like, because it's in the same under the same interface, same graphical interface. So the idea here, the main idea here, is for you to have a single software supplier for either durability or signal processing, or even now acoustic analysis or vibration analysis. So in terms of the benefits of the software itself, the idea is to easily build an analysis workflow, easily understand what this workflow that you got from your colleague, for instance, or that you opened up, so therefore easily understand what this workflow does. It's easy to maintain, it's easy to make it generic, so we're improving the consistency and the quality of the results throughout a company. And basically, thanks to this to these workflows, to these graphical workflows, one can go in one click from the raw data to the report, to the final report. So using this graphical interface where glyphs are connected together with pipes to displays, etc., allows you to save time and therefore costs, because everything goes easier, faster, and more confidence in the results. So in terms of the features, we'll discuss about three main applications. The first one is rotating machinery. So within VibeSys, we'll see that we've got quite a few features, quite a few analysis capabilities for rotating machinery analysis. Another one is human perception of sound and vibration. So that's also called psychoacoustics when it comes to acoustics, right? We'll see that we cover a few standards, and we're able to rate or say to characterize the level of the sound and vibration, the way the human receives it. Structural dynamics is the third application, where we want to characterize a structure in terms of its dynamics, modes of resonance, etc. Then we've got a vibration manager. I'm just going to say a word about it. That's a database, if you like, where we've inserted the most used spectra in various international standards or national standards, military or public. And the idea is that you can easily enter your own qualification spectra for comparison purposes, etc. So that's the vibration manager. So we'll see that within VibeSys, we've got quite a lot of those glyphs, or in other words, those analysis functions, features, and if needed, if you still have, if you still can't find the analysis that you're specifically looking for, you can code it, you can create your own glyph using Python or MATLAB. So that makes it very extensible, very generic for a corporate tool. And one of the biggest strength of this product is that it can easily analyze gigabytes of data, and especially if we're talking vibration and acoustics. We often have long signals at a very high sample rate, many channels, so that's absolutely no problem for VibeSys. So let's start with the first application that I mentioned quickly, rotating machinery analysis. So any rotating machinery such as a thermal engine, electrical engine, a turbine, a gearbox, anything that rotates generate vibrations, and if there is some defect or some wear, any kind of fault in there, misalignment, imbalance, things like that, they have their specific signature. So here with the modules, a part of the rotating machinery palettes that we're going to see in a minute in VibeSys, we can easily detect those signatures. So in terms of features in there, we've got a glyph that does the pulse to speed conversion. So if the speed of your shaft is given as a train of pulses, like 1 pulse per revolution or something like that, we can convert this into an RPM signal, and this feature, this pulse to speed glyph, has many options, properties for error checks and smoothing. Therefore you end up having a very smooth RPM signal, which is fundamental for the upcoming analysis. One of the analysis that requires this RPM signal is the waterfall analysis, where you have a vibration signal or an acoustic signal, say, and an RPM, and you're trying to understand, figure out what the relationships are between the speed of the shaft and the vibration that you can feel or hear. So that's a waterfall analysis, and it ends up with a nice waterfall plot, just like the one that's on the top right of the screen, where we can clearly identify those lines that we call order lines. These orders can be extracted graphically, for instance, or using some algorithms, and they can be extracted under the form of slice spectra to be compared, overlaid, etc., or under the form of the time domain. You know, the time waveform can be extracted also, so that enables one to replay the whole signal, re-listen to the whole signal, and to the whole signal without a specific order, or to attenuate a specific order. So that enables you to do sensitivity analysis, what if sort of games. For more accurate order analysis and waterfall analysis, some of you may prefer resampling the original signal into the revolution or into the angle domain. So that's feasible. There's a glyph for that, and therefore you obtain eventually a spectrum in order, no longer frequency, but the x-axis is order. Similarly for waterfalls, and that's very very accurate, generally speaking, because we get rid of all the of many of the assumptions that Fourier requires. And we get rid of artifacts such as smearing, etc. So all these spectra and waterfalls can be displayed, obviously, in VibeSys. So we've got the color maps to display the waterfall, or the Campbell plots, such as the one displayed on the right, bottom right of the screen here. Sometimes it's clearer to look at Campbell, because you only see those circles represent the high energy peaks, you know, in the waterfall, and it's sometimes clearer to spot an order this way. This Campbell plot is quite interesting, because you can also enter the coordinates of this green line, for instance, to follow to track maybe something that's non-linear and understand non-linearities. Other features for troubleshooting include the Capstrom analysis for identifying sideband frequencies, the Hilbert Transform, so that's for demodulation and understanding well the modulation function created by some particular flows or some particular, say, defect in bearings, for instance. We've got indicators such as the kurtosis, whether it's a global one on the signal or running kurtosis, etc. All this again for troubleshooting rotating machineries. Another interesting application in VibeSys is to do with structural dynamics. So we want to characterize a structure knowing its excitation and its response. So there may be many excitations, many responses, and for each couple of excitation response we get this famous frequency response function, which is a spectrum indicating specific frequencies that are amplified due to modes, for instance. So this can be displayed under the form of a gain spectrum. We can display the phase, the coherence, and the auto and cross spectra. A nice feature is the ability to represent this FRF under the form of a waterfall. So here we've got many FRFs that are displayed along the time axis, and that's used typically to understand whether there are non-linearities in your system. So for instance, if you're doing a shaker test and you gradually increase the level of the excitation, if everything's linear, well, the response should see its level increasing proportionally. So in the gain FRF, the gain FRF should remain constant. If it's not linear, you will see some increases or decreases of the amplitude. You would see some changes in the natural frequencies here. So no longer a red line, but some sort of curve. So that's a nice and easy visual way of identifying nonlinearities. We've got several ways of applying an FRF as if it was a filter to an excitation signal, such that once you've characterized the dynamics of your system, once you've made sure it's all linear, you only need the excitation signal and the FRF to compute what the response would be. So we've got a custom filter enabling you to not necessarily only have a low pass type of filter shape or high pass or band pass, but the filter shape could be this red FRF, for instance. We've got a convolution a glyph available as well. So this time we're going to filter an excitation signal using the impulse response function, characterizing the dynamics of a system. We've got other features such as auto and cross correlation that can be useful to understand hidden periodicities in signals and features that are reproduced every so often in a signal. We've got a Hilbert Transform again that we're going to use here, but this time it'll be useful to find the damping ratio from an impulse response function. I'll illustrate that in a minute during the demo. And we've got cursors that you can apply on both waterfalls, but here mostly we will use them on the FRFs to understand what are the model frequencies, and via horizontal cursors we can derive what's the minus 3 dB delta F, and therefore the damping ratio again. So the last application is the human perception to sound and vibration. So if we start with vibration, we've got the whole human body vibration indicators. That's compliant with the ISO 2631 for the whole body, or the ISO 5349 for the hand-arm vibration. So basically we are applying weighting filters to vibration signals, and we extract some indicators such as the RMS, the global weighted RMS, in various directions, the crest factor, the 8 hours combined vibration value, the 8 hours vibration dose value, etc. We can display an octave or third or sixth octave spectra from a time domain signal, or from a PSD or waterfall, in either linear or dB scales. And in terms of acoustics, it's very similar. We've got weighting filters, the famous A, B, and C networks that we can apply to microphone signals. And once done, we can either calculate some octave spectra or some indicators such as the continuous sound equivalent level, or the LAF max, SEL, LAE, etc., etc. Again, with the filters we can apply include an order tracking filter, or all sorts of filters, and that enables the user to remove from the signal some specific patterns, or some specific results of some dynamics or rotating machinery, and re-listen to it and recalculate those indicators and figure out what to do to optimize the acoustics or the vibration levels of a system. So some of you may be familiar with GlyphWorks. So GlyphWorks is a signal processing package that we have, and it's very much oriented towards durability. Now, VibeSys is similar in terms of GUI, but again, it's dedicated to acoustic and vibration. So it's got dedicated worked examples, such as the ones that are listed here that you can see. Worked examples like how to calculate a frequency response function, how to calculate a waterfall, how to calculate the indicators for acoustics, etc. It's got standard processes like the ones that are displayed here, listed there. So you've got, for instance, a standard process that does the comfort evaluation according to ISO 2631. It's all built, ready to use. You just have to open it up and press, drag your data in and press run for it to give you the final report. We've got a theory guide that tells you what an FFT is, how to what are the important settings, and how to derive, how to extract an order, etc. And we've got also a user guide. In terms of usability, the nice thing is that well, if you use GlyphWorks with the VibeSys option, you'll have one palette that's now called VibeSys, and which contains all the glyphs for VibeSys. If you click on the new VibeSys button on the menu on the left hand side, the collection of palette is somewhat more usable. You've got more palettes, right, containing the dedicated glyphs to dedicated analysis. So it makes your life easier to find a glyph, and again, all this makes this VibeSys software more dedicated to acoustic and vibration analysis. So it's time now for a demo. Let me just fire up my my VibeSys. So that's a flow for acoustic analysis that I've created, an example flow. I've pressed the VibeSys button here, so I've got the VibeSys palette here. As you can see, the collection of palettes is a bit different from the one you may be used to know in GlyphWorks, right? So here the flow I've got is indeed on acoustic. So I've got a microphone signal in pascals here, and by pressing the run button, I'm obtaining this final report with an octave spectrum and some other spectra here, some indicators here, and so that can be exported in PDF, PowerPoint, Word, whatever, image, very easily. Say these indicators are above your standard, or above the threshold, the maximum threshold you wanted. You can figure out what to do, So the first thing you probably may want to do is listen to those signals. So let me do that now. I'm going to use this glyph here to listen to the time domain signal. I've got a cursor moving onto the signal, showing me where we are. I guess you can hear that. Maybe you can hear that. And I got a feeling that looking at the time, let me stop that now. Looking at the time frequency plot here, I may have the feeling that the noise that I'm hearing is related to the RPM. It's an engine. Signals coming from an engine, obviously. Maybe that was clear to you, but sorry, I didn't mention that before. But it could be obvious to me that the noise, the general noise, is related to the RPM. So that's where we want to do an order analysis. So let me do that now. Run that now. I'm first resampling everything into the angle domain, and then I'm doing a waterfall analysis. So here I'm getting my order-based waterfall, on top of which I can use cursors to extract some of the orders that are displayed here below, so I can understand which order is preponderant, is dominating, say, in various speed ranges of speed. So if it happens that a specific order is dominant, you may want to filter it out from the signal. So that's what's done here with the order tracking filter. You can remove order 2, order 4, or whatever order from the signal. And here what I did is a classical waterfall of the whole original signal and the waterfall of the signal without 2 orders that I've removed that used to be here, right? And the nice thing, so the obtained signal, the nice thing is that I can re-listen to this obtained signal and see, you know, subjectively, you know, I can tell whether it's easier to support or to stand, you know, or not. And I can also recalculate all those indicators and spectra, you know, from this filtered signal, and therefore understand what is causing those high values in terms of LAQ or LAF max or whatever. So that's pretty much it in terms of acoustics. That was just an example illustrating both the acoustic capabilities, some of the acoustic capabilities, and the filtering and the waterfalls. I've got another example for you which deals with the structural dynamics. So here, for instance, I've got an excitation signal in red and a response signal in blue. And what I'm doing here is I'm calculating its frequency response in both gain and phase. So again, I can use cursors here to identify the modal frequencies from my spectrum here, the phase that's associated with it. I can zoom here. I could add another. I could add a vertical, horizontal, sorry, a cursor here and understand what's the delta F at -3 dB, half the power here, things like that. To illustrate another feature of this frequency response analysis glyph, which was the waterfall of FRFs, I'm using this new workspace, same signal, same glyph, but the only difference is here, and the analysis method is no longer the overall one, but it's the waterfall one, and therefore I can run this and look at this nice waterfall spectrum and see whether it is changing with time, throughout time. And the last thing I wanted to show you is the use of the Hilbert Transform to figure out what the decay rate is, and therefore what the damping coefficient could be. So that's an impulse response function. So the structure was excited with a hammer, for instance, and we've collected some response signal at a specific location. So if you do the FFT of that signal, you'll find the FRF actually of your component at this very location. Now let's focus on one particular mode, for instance this one, which is around 70 Hertz. Yeah, that's it, 70 Hertz. So what I did here is I band pass filtered around 70 Hertz, and on the filtered signal I ran a Hilbert Transform, which is taking the envelope of that signal. This envelope is displayed here, and if you displayed it in log axis, you'll find out that it's a straight line, and using cursors again we can figure out what the slope of this line is, and therefore what the damping ratio is for that particular mode. So I think that was it in terms of presentation of VibeSys and demo. So if you're interested, feel free to contact your account manager. If you got any technical question, don't hesitate to send me an email. I'd be happy to try to answer your questions. So thank you again for attending, and I hope to hear from you soon. Thank you very much. Goodbye.